Hi everyone, I'm Chris. So I'm going to be showing you guys a project I worked on back in school. It's called Friendnet. The goal of this project was to build a model from scratch, and the model will be able to classify my friends' faces. And so I built this model from the ground up. So what this means is I did the dataset collection, made some videos of my friends, extracted some frames out of these images, prepared them for input, did some transformation, converted them to tensors, and all the processes that go into feature extraction for your models. Then I built a custom CNN model. What CNN means is CNN is CNN is called convolutional neural network. It's an architecture in deep learning. In deep learning, it helps you, it's for vision models. Not just vision, CNN works across different dimensions. There's the 1D CNN for audio, if I'm not wrong, 2D, two-dimensional CNN, that is for images, and three-dimensional CNN, that is for videos. So I work with the two-dimensional CNN architecture here to build out my own custom model, Friendnet. And I trained across 5,000 images of each of my friends. And anyway, the presentation I'm going to show you runs through from dataset collection to inference with FastAPI, and we'll run a quick demo to show you how everything works. So, by the way, side note, I will raw dogging this video. Some of the concepts I might not clearly state it right, so we'll learn together. I'll open a side browser or ask questions and understand each concept. So we are learning on the go. Friendnet. Like I said, it was built with a custom CNN. Each image was normalized and ready for inputs to my models. And network patterns was used to extract faces, feature extractions, and the final layer was used to do some classifications using softmax. But let's do a quick dive on so you understand what CNN is. So CNN email. So CNN is a specialized way of deep learning. Like I said, deep learning algorithm primarily used for analyzing, processing grid structured data like images and videos. So for CNN, the concept of CNN, it's there are different concepts inside CNN. So there's the kernels that slide through. Anyway, to understand this better, I'll just say go look up CNN and understand how it works. So CNN tries to stride through your image data and extract features for each of them. Let me see if I can. Mail backlog. Yeah, CNN explainer. Yeah. So this is CNN explainer. So you can see if you click on this, you see, or like I said, it strives through each of them and brings out the feature for each of the images. Now, the deeper you go, the more features it extracts. Now, there is also the concept of ReLU, which is the activation layer. It takes out some of the features better. So ReLU takes max of 0 and the number. Okay, let's understand, because how does ReLU work? Rectified linear unit is an activation function used in artificial neural network, used by transforming the output of a neuron so that all negative values are instantly converted to 0 while positive values. So what this really does is it takes, as it strives through, it takes out the more prominent features out of this. So as it strives to, it takes out only the important ones. So where the colors are much more permanent, it takes it out and brings it out for your images. It's also part of features extraction. So for CNN architecture, there are for deep learning, not CNN. For deep learning architecture, there are three parts of your deep learning network. There is the input layer where your inputs inputs are sent in. There's the middle layer, which is the extraction, where the extraction happens, and the output layer, which you can either use your ReLU, you can either use your softmax, binary classifier, or whatever classifier you're doing, or whatever concept you're trying to build with your architecture. So for this project, I worked on supervised learning, image classification, feature extraction, like I spoke about, and transfer learning. So I didn't just work on my CNN, I didn't just work on a custom CNN Friendnet. I used two other models, the ResNet50 and CLIP. The ResNet architecture is one of the base version of most of the vision models that exist currently today. And it was trained on ImageNet. And ImageNet was founded. ImageNet50. ImageNet is a vast, it's a big, sorry, let me just give you ImageNet dataset. ImageNet is a massive human annotated image database organized by WorldNet hierarchy. It was founded by Feifei Li. So ResNet was trained vastly on ImageNet, so it has a lot of feature extractions. So transform learning I'm talking about is I use ResNet50 to train on my own images. ResNet was trained on ImageNet, so I just used it because it has good feature extraction. I used it, I froze its 50 layers and only worked with the last layer, which is the classifier. Same thing for CLIP. CLIP was trained on more than 400 million images by OpenAI, if I'm not wrong. So let's look at transfer learning. Transfer learning is a machine learning technique where a model developed for a specific task is used for that as a starting point for new and related tasks. Like I said, I used transfer learning and I used ResNet. So ResNet was trained on ImageNet, and ResNet and CLIP are trained on different image. They also trained on image, so they are trained on a specific task. But I used it because their models can be used on a related task, which is I'm also training on images extracted from videos, which are frames. So I used the models and replaced their classification head with mine because I needed 5 classes and changed the classification head to what I needed, and it's removed and froze up the other layers because I don't have the compute to train fully on ResNet or CLIP. Anyway, the presentation will give you a glimpse of what happened. So image, preprocess, feature, class calls, and prediction. So like I said, I worked on Friendnet, ResNet50, CLIP. Friendnet learns directly from friends' images, so it has to discover useful filters from this project. Like I said, that's what CNN does. ResNet is also a CNN architecture. It helps with image recognition knowledge from ImageNet, like I said. Then Abdas is final classifier to 5 friends, exactly. So CLIP turns each image into rich embeddings, so it's not classified. I think CLIP is a vision model. Let's confirm that. CLIP by OpenAI vision model. Contrastive language image pretrained is a foundational vision language model developed by OpenAI that connects image and text. So originally, CLIP is meant to convert, I think it's a captioning, types to caption video, meant to caption images. It works in relation to text. So text contrastive language image pretrained. So it works. So if you're describing a text, it could map that text to your image. But I only worked with the image part of CLIP. It's a vision language. So one of the reasons for Friendnet is for security, social media tagging, personalized systems. And my friends' name were Osama, Uzaya, Jacob, Luke, and using deep learning. So I used Friendnet to classify these 5 different faces: Tatiana, Uzaya, Jacob, Luke, and Osama. And like I said, some of the applications were security, social media tagging, personalized systems. and recommendation systems as well. So a typical example is you're having a party and you want to invite your friends. You can simply mount your model to make you accept the friends that recognizes their faces instead of having to employ security. Please employ security. Yeah, I shouldn't take over that job. Next, dataset preparation. I told you I use 5K images split into 700 for training, 150 for validation, 150 for tests. So what validation does is to help us understand how the training is, how good the training is going. So as the training happens, validation helps to tune the parameters better and let you know if the training is doing what it's supposed to do. Again, we can learn together. What does validation step do in ML? Validation step acts as an unbiased checkpoint during model development. It evaluates how well the model generalizes to unseen data and allowing developers to tune settings, like I said, and prevent the model from simply memorizing the training materials. Yep. And like I resized the frame to 224 by 224, normalized it to. Why this normalization is this? Because ResNet was trained on this particular normalization for its tensors with ImageNet. So when you're training or doing transformer learning with ResNet, you have to be careful to use the right normalization. If you check the documentation on ImageNet, you should see the right normalization you should use for ResNet, or ResNet documentation, you should see this. So for augmentations, I changed up the images for color jittering resizing shift. This kind of gives a typical life real-time image. Say for an example, your friend came in at night, like Tatiana's face here is a bit dimmed. So imagine your friend came at night. You want your model to also know what your friend looks like at night. So that's what augmentation does. I apply some different augmentation on different faces, so a model can be generalized on different angles, lighting, and backgrounds. Yeah, how it reference frames were extracted from short videos, so there are enough samples for each person. Resized to 224 by 224 augmentations were applied as well. So train validation test with normalization, class, balance, augmentation. And model architecture, I told you I used my custom CNN, which had 3 layers and 64, went from 64 channels to 128, so from 128 to 256. What channels are like stages of feature extraction? And the last layer from the channels, we went down to 5, 12, and 5 classes. And badge norm is all these are ways to optimize your models so they don't generalize. Max pooling, reload, dropouts, also their generalization techniques. And I told you I used ImageNet. Wait, let's confirm if we're still on the meeting. Yeah, we're here. So I used ImageNet, modified the final layer. It has 1,000 classes from ImageNet, and I reduce it to 5 for what I need. OpenAI's CLIP with linear classifier for 5 classes, multimodal pre-training for robust training. So I did some explanations here. Custom CNN evolution can scan image with small filters, like I showed you guys on this place, the filters that we are scanning right here. Yeah, not here. And each filter catches edge, color, changes middle layer, combine them into eye, hairline, blah blah blah. So it just extracts features that we can't see with our eyes. And ResNet, the model is much more deeper. The residual connection lets each block learn small correction stuff, renaming the whole image representation. This helps gradients move through. CLIP also a training model face. Basically, all these things help with feature extractions that would be used for classification. The project can use its image embedding as a strong summary of face, then classify that summary. Freezing means keeping pretrained layers locked during training. Like I told you, I froze ResNet's layers and click because I don't have the compute to train on the entire model. And their weights do not change, so only new classifier heads learn. So like we did there, we removed 1,000 and used only 5 classes, the final layer. And same thing was done for CLIP. And The training process, hyperparameters, I used the SGD, stochastic gradient descent. My learning rate was 0.001. Momentum was this to avoid spikes. Then I use cross-entropy loss because there are multiple classes here. Here I trained on 30 epochs with early stopping of 10, so we don't overfit. I trained on A100 on Google Colab. And the process training loop with that badge of 30 and validation after each epoch. So forward pass sense in badge of images through. So there are a lot of concepts here that we need to break down. Anyway, cross entropy punishes the model when the true friend does not exist. That's the loss. So the basic knowledge you should know for loss, when you anytime you hear loss, is like a punishment for your models. So if, for an example, your model predicts something wrong, the loss will punish it and say this is wrong because it's too high. I think the base versions of loss concepts are the MAE and MSE, mean squared errors, I mean absolute errors. Let's just ask what MAE. Means absolute error and MSE are core mathematical metrics used in machine learning to measure how far a model's predictions are far from the actual truth. So they quantify model accuracy and serve the objective function that optimization algorithms like gradient descent minimize during training. Gradient descent is quite a huge topic. It's the reason why most models work today in machine learning, and I've quite broken down most of these concepts on my blog. Yes, and give me a sec. So if you go down here, view of stories, understanding machines, you see I broke down some concepts: neural network, gradient descent, deep learning, hidden layers, backpropagation. So most of these concepts are quite explained on my website. So, and they're broken down to the base version so you understand how it works. Okay. So early stopping helps to prevent the model from blindly trusting final epoch or overfitting. So when the validation step starts getting plateaued, early stopping comes to stop the training from continuing to avoid overfitting. And performance, the model is performed quite good. But I remember my professor telling me the reason why the models were so good 100% was because my friends, they have distinct faces. So it's quite easier for the model to catch their faces and classify properly. So if I try to use people that looked kind of similar, this model, the accuracy won't be this good. So, but the precision recall helps tell whether the model is confusing one person from another. Pre-trained models usually separate. So these precision recall are used for classification and help you to know how good your model performed. And for reported test performance, Friendnet 95%, ResNet 100%, and CLIP it's 98.87%. And the training loss, the loss and accuracy curves, you can see. I'll put the link for this project presentation, and there's also a download PPT link here. You can download the PPT and look at it for yourself. This is the link to the presentation. I'll put it here. I need us to dive to the demo because this video is getting quite long. I'll spend so much time explaining how loss and accuracy works, why training loss drop means the model is fitting. Okay, I think this is good. Training loss dropping means the model is fitting the examples the examples it sees during training. Validation loss dropping means the model is also improving on held out examples. And if training improves by validation, guess what? The model is memorizing things that do not matter. So from this, you can see the model did a good job. And if you zoom in, yeah, you zoom in. Oops. Anyway, you can get this from here. Okay. And this is the model explainability. I use GradCam to see what the model saw during training. See it focused on Jacob's face, Tatiana's face, Luke's, bit of Luke's neck. It didn't really catch his face. And Osama's hair, his eyes and mouth, and Uzaya's entire face was properly caught on his attention heat maps. GradCam helps explain what part of the image influenced the model. For face recognition. A useful heat map should focus on the face, not the background, clothing, room lighting. So like I said, Jacob, Hosea, Osama, we got a bit of their face. Webcam checks which late feature mattered most for that label, and yeah, explainability feature map, class activation, and model debugging. Webcam is usually used in the sense in case you want to understand how your model performed or how your model, what your model sees during feature extraction, or why it chose what how it's worked to give you predictions you have. Anyway, you can still ask those grab can help it. GradCam gradient weighted class activation mapping makes black box deep learning models, specifically convolutional interpretable by generating visual heat maps that reveal exactly which parts of an image the model focused on to make a specific prediction. Yeah. So conclusion, ResNet achieved near perfect accuracy. Friendnet performed well. Balanced dataset. The classes were balanced because I made sure I did documentation to boost up the imbalanced ones. Feature work advanced, augmentation, increased dataset diversity, test ensemble. For the demo, let's do a quick demo. So this was previously deployed on Friendnet, but I don't have it's quite the project has been stale for some time and I've been charged a huge amount of money just for keeping the project there. So it's currently hosted locally, and if you'd want to test, you can always reach out. If you want a quick demo, but this demo should show how my project works. Also, yeah. Anyway, so for the demo, you choose the models you want to try. I'm choosing the 3 of them. You choose your image. So I'll start with a group image. It gave Uzaya as the ensemble prediction, but single models, Uzaya 96%, Osama has the most here, and Jacob has the most here. But you see, CLIP managed to catch our faces. Everyone, there's a certain percentage for everyone's face on this prediction from CLIP. Means CLIP is the most accurate when it comes to group image classification. So let's clear this and try a different one. Mind you, what I'm trying are unseen images during training. I didn't use most of this. I didn't use any of this image during training. So let's try Jacob. Perfect. Jacob was caught correctly. Again, my model didn't do the right thing. It's still seeing Jacob as was there. Jacob here. ResNet got it. CLIP got it. And let's clear and try Tatiana. Hopefully this should work. Yep. My model performed very well on Tatiana. ResNet didn't perform good, and CLIP did. way good. I think CLIP has been the most accurate in this project. So the reason for this ensemble prediction is we don't depend on just one model. We depend on the answers from 3 of them. So imagine we depended on only ResNet, we wouldn't have gotten the right answer. For Friendnet and CLIP gave us the good answer, and we combined it and have this. Also, the last prediction we did, Jacob, my model didn't get it right, and ResNet and CLIP got it right. So ensemble predictions help to give a cumulative probability of the right answer. So let's try one more. Who's there? Let's try who's there. Yeah, this review is there. Again, my Friendnet model only got Tatiana right, and ResNet got it right, CLIP got it right, and there again, another reason why ensemble models, ensemble answers are usually good. Anyway, this is the project I worked on my second semester at Fanshawe with my deep learning with PyTorch class. I hope this helped to give you a little breeze of how CNN works, transfer learning, freezing layers, CLIP, some other concepts. And I have some bookmarks here that could help anyone looking into ML. Yeah. Thank you guys, and see you on my next video.